right, so it's a pleasure to welcome back Zaki. Zaki was a PhD student here. He spent 3 years in China, and
Yes.
he's now in his second year of a postdoc with Susan Gardner at the University of Kentucky. He was, I think, one of the first grad students who I worked with, so it's really special to welcome him back. And please, the next time you're anywhere near the West Coast, you will properly come back and we will have a proper speaker dinner. Right, so,
Sure.
Zaki.
I will. So thank you so much for the introduction, Flip, and it's nice to see all of your faces again. Yeah, I do miss California. Hope to see you guys soon. And thanks for the invitation. As you know, I'm going to talk about constraining baryon number violation using neutron stars. This is based on a work with Jeff Berryman, who's also online, and Susan Gardner. Part of this talk is already published, and you can find the archive number written here. But part of it is in preparation. We hope to have the results ready soon. So I just want to give you an outline of the general topics involved. It's a wide range of topics. On the particle physics side, we're obviously interested in models with baryon number violation, the model building of it, dark matter models with baryonic charges, let's say. And we're also interested on the experimental side, mainly neutrino experiments like SuperK, which give us really good limits on baryon number violation in the nucleonic sector. And in the strange sector, we used the experimental data from high-prime factories, which I'll talk a little bit about. Of course, since we're dealing with neutron star matter, it involves some nuclear physics, and we have to assume some sort of dense matter formalism if we are to calculate rates. The main thing here, the main uncertainty on the nuclear physics side is the neutron star matter equation state, which is still an open question. And obviously, we also deal with real astrophysical objects, pulsars, or binary systems. So I'll just briefly talk about the particle side, just to motivate. Baryon number is an accidental symmetry of the standard model, which is also linked to the apparent stability of matter. And yet we do know from theoretical motivations that it has to be violated at some point. The famous examples are grand unified theories and baryogenesis models and their variation. These models usually come with some sort of rare signature. For example, the famous one is proton decay or N bar oscillation, which can then be constrained using neutron experiment results. So I will quickly talk about some of the experiments. The first one is SuperK. It's a Cherenkov neutron detector. It has about 10 to 34 nucleons in it. It's filled with water, and so we can probe the Cherenkov radiation from any interaction with electrons or nuclei of water. So the Cherenkov radiation hits the walls. There are photomultipliers on the wall, and based on the ring that you get projected on the wall, you can identify the generic type of the particle. If it's sharp, you say it's muon-like, for example, and if it's fuzzy, it's electron-like rings. And specifically, I want to cite this limit that you see. It's a limit on neutron decay to neutrino and a photon. So obviously the limit is amazing. It's 10 to 32 year on the lifetime. But the photon is detected and there is an energy cut here involved. So it has to be at least 100 MeV, the Cherenkov ring that's detected associated with photon, which means if you were going to use this to limit a new physics channel, a neutron decay to chi, which is a dark particle, plus a photon, you can choose the mass of chi to be heavier than 839 MeV, and this limit wouldn't apply. Okay, because in that case, the photon's energy would be below the cut, so we wouldn't be able to set this limit. So it's just an example of being aware of the limits of the constraints. The other experiment I want to mention is CAMLAND, especially because they were able to constrain single neutron and dineutron disappearance to invisible. So they're able to get this amazing 10 to 30 year limits on inclusive anything invisible channel because they're using a nuclear de-excitation signal. It's a carbon-12 that gets de-excited. It gets excited and then de-excited. And then the way they eliminate background for these specific channels is that there are actually 3 signals that are correlated spatially and in time. And they also have energy ranges, so energy cuts. So when you combine them together, you basically eliminate background, and that's how they're able to get these limits at 90% confidence limit. So they're pretty good nucleonic limits and pretty constraining. But I just want you to keep in mind the order of magnitude, which is 10 to 30 year for now. In the strange sector, we obviously have an issue, and that is that hyperons are obviously less abundantly produced and they are short-lived. So any terrestrial limits we're going to get, they're going to be much weaker. Here, I'm just citing 2 limits, one from class at JLab, where they actually observe, they look at the decay, baryon number violation decays of lambda hyperon to a charged meson and a charged lepton. And you can see the limit on the branching ratio. I just translated that to a lifetime so you can compare it with a nucleonic limit. You see it's about 40 orders of magnitude weaker than the nucleonic limit. The other one is the Beijing spectrometer, where they actually have E plus E minus collider. They produce a lot of Jape size, and then it decays to a lambda bar. They can detect the lambda bar, and if they don't detect anything else, they assume that lambda decayed into invisible channel. And so they're able to get inclusive limits on lambda decays at this order that you see. Again, same order of magnitude in the strain sector, but 40 orders of magnitude worse than nucleonic limits. Okay, so for the rest of the talk, I'll focus on neutron stars. But before I start that, I want to mention this work that has been done on using supernova SN 1987A to constrain hyperon dark decays. So they basically consider this operator, which connects the strange quark with the other quarks to a new dark particle that carries baryon number. And the idea is that if this dark particle, chi, is produced in lambda decays, that part of the spectrum that has enough kinetic energy that can escape the gravitational potential of the protoneutron star would actually be able to drain energy from PNS, which is an exotic cooling channel. And we know that any new cooling channel for supernova is constrained by the neutrino signal. The duration of the neutrino pulse, it would affect the duration of it. And so they use that to limit branching ratios for some specific models. Obviously, these branching ratios depend on what mass you choose for chi. This is just for their benchmark points, some average value for chi, imagine. I'm curious here about the order of magnitude, really. So these limits a little bit better than, let's say, the invisible limits that are terrestrial from Beijing spectrometer, but still, first of all, they're model dependent. Second, they're still 40 orders of magnitude worse than the nucleonic limits. Okay, so that's the general situation when it comes to the limits on both strange side and the nucleonic side. So the question I want to talk about today is, can we use neutron stars to constrain B and V? And obviously, I want to work in a model independent way. So neutron stars, this is just a toy picture of what a neutron star looks like. They're on average 1.4 solar mass. They're very compact with an average radius of 12 kilometers. which means you have to use general relativity because there's a lot of mass in a small space. We observe mostly those neutron stars that are pulsating, so we see them as pulsars that rotate at a rate of periods of millisecond to second. They have about 10 to 57 baryons in them. So obviously it's a huge tank of baryon, much more than what we have at SuperK. And they have their central densities could be much larger than 0.16, which is the saturation nuclear density for the heavy neutron stars. And their temperature, once they're born, they're pretty hot, but their temperature keeps falling down much below 10 to 10 Kelvin, which is MeV, and so which is much lower than the Fermi energy. So we have a really cold, degenerate gas of baryons, basically, with some leptons. The existence of neutron, proton, electron, and muon is not really something that people doubt. We already know that they're there. The question is really, what do we have in the core? And because we don't access those densities on Earth, it's hard to actually know what exactly is, what are the constituents exactly in the core. Hyperons are one possibility, but it's an open question. You can also have quarks in the core and hyperons. You could have the different phases, but that's why I put the question mark there. So I just mentioned we have to use GR. Here, we're just using the most basic model, which is a spherically symmetric static metric with a static perfect fluid. So this is the typical thing. Of course, you can consider the corrections to this from rotation and other things, but to first order, this describes things pretty good for the general structure of the neutron star. And so the point is that after you solve the Einstein equations, you get the famous Tolman-Oppenheimer-Volkoff equation, or TOV, which is basically a differential equation that gives you the pressure as a function of radius that has to be integrated numerically. And then baryon number is defined as usual. It's in GR, so you just have to be careful. It's a conserved current in GR. You just use the covariant formalism for baryon number. Okay, so I already mentioned that neutron stars cool down to temperatures much below their Fermi level, which means you can, at least for the general structure of the star, you can ignore temperature. Basically, you can set it equal to 0. So when you write the equation of state, which is what describes the fluid inside the neutron star, you remove temperature. So equation of state is the relationship between energy density and pressure as a function of the baryon number density. There are many choices of equation of state that give you the same or almost the same mass and radius for neutron stars. And at this point, most of them are valid, basically, from experiments or observation. The structure of neutron star, meaning the functional form of energy density and pressure, are found by integrating the TOV equation with some central value, some initial value at r equals 0, which we call epsilon c, the central value, all the way to the surface where the pressure by definition is 0. Now, because this is a differential equation and it has a unique solution, then it means that for any choice of a given choice of equation of state and a choice of epsilon c, you get one unique answer, which means if you keep varying values of epsilon c for a given equation of state, you get a unique family of neutron stars. So that's what's called single parameter sequence of stars. So every equation of state comes with a single parameter sequence, basically. Here for the presentation today, I'm using this equation of state from Dexheimer and Schramm. It's a chiral mean field model. They have different variations. This is just number 1. They do include hyperons in their Lagrangian, so we do have hyperon degrees of freedom in neutron stars. And then just the last comment, you could make this more complicated. You could think about rotation, or you could add a dark degree of freedom, independent degree of freedom. That just adds to your parametrization, basically. So you have to provide all those to be able to describe the stars uniquely. But for the simple scenario here, we just look at the one-dimensional parameter sequence. Before I move forward with our analysis, I should mention something that comes up a lot, and that is the question of hyperons in neutron stars. Do we have hyperons in neutron stars, or in general, or no? It's still an open question. They are naturally expected to show up at high densities, between 2 to 3 saturation. This is because the baryon chemical potential keeps increasing with density, and at some point, baryons would be able to convert to lambda and sigma minus, for example. And so they are naturally expected, but they also come with some issues, the so-called hyperon puzzle, for example, because if you include them without some careful considerations, you might end up not producing heavy enough neutron stars. So that we already know that we've observed, let's say, 2 solar mass neutron star. So you could write models that have hyperons and produce 2 solar mass, as I'm going to show you. But it is still an open question whether we do have hyperons or no. In the future, if we can limit the hyperon nucleon and hyperon interaction potentials, that would actually tell us something about whether they're favorable or not. At this point, it's not enough for us to know. But here I'm just showing an example of a direction for future that's ongoing right now, and that's the hypernuclei experiment. For example, you can use kaon-pion beams to change a nucleus into a hypernuclei. It will turn, let's say, a neutron to a lambda-sided nucleus. And then if you measure the charge meson on the right-hand side of equation 6 and 7, by measuring its energy, you would be able to get some information about the binding energy of the hypernuclei. And we know we did already produce a lot of lambda hypernuclei. So that tells you that this must be an attractive single particle potential for lambda. And the estimate for the potential of lambda at saturation density is about minus 30 MeV. But we haven't observed anything with sigma minus, which tells you that it has to be repulsive. There has been a few candidates of Xi, which again tells you it's attractive, but the error bars are big, and more experiment has to be done on this. So one question is that's important to address here, that's not being addressed yet, is lambda-lambda interaction. So for that, you would need to at least produce a double hypernuclei, which is much harder to do. Then that would tell you something about the lambda-lambda potential, for example. So this is an ongoing direction in a lot of like heavy ion colliders or proton accelerators. And so hopefully in the future we can settle this. But for now, it's not clear what's the final solution. My favorite answer is that we do have hyperons, but we also get some quark core that doesn't come with the other issues of hyperons. But we can talk about this more later. So this is what the one parameter sequence looks like for this choice of equation of state. I'm showing all the macroscopic observables of the stars in the same plot, so I made them dimensionless for you. I divided them by some average value. The purple curve shows the radii. The orange curve shows baryon number in units of 10 to 57. Mass is in blue in solar mass, and the green curve is moment of inertia. And I showed with the dashed line the range of densities or masses of stars that would start having lambda hyperon or sigma minus hyperons in their cores. So you can see that with this equation of state, you can get hyperons if you look at the heavy neutron stars. So, okay, now back to the baryon number violation analysis. Ideally, generically, you have your favorite baryon number violation model. You add the new physics term in the Lagrangian, and then you would have to convert that in terms of some in medium rates in the star, and then you would have to integrate it, manipulate it, and translate it in terms of some macroscopic change of parameters. And then you would relate that to some direct observation. So what I want to do is, I'm not interested in having a situation where for each model that you write down, you have to do an analysis from the start. I'm trying to find the conditions under which the direct observables become independent of your particle physics details. So that's what I call model independence analysis here. So I want a picture that looks more like this, where you have your particle physics. For example, you say I added a dark particle chi, and I predict I'm going to have lambda decays to a chi plus a photon. Let's say this is its rate in vacuum, blah blah, and I can translate that in terms of a medium rate. But our analysis will do the rest basically. So we'll start from some observables, and we limit the rate of change in the total baryon number. And so all has to be done is to translate the limit on B dot to the particle physics rate later. Okay, so I kind of disentangled or separated the limit on B dot from everything else here. So in order to be able to have model independent analysis, we first have to check what are the model dependent effects and try to get rid of them. So the first one is that obviously the star is going to respond to the BNV perturbation. If you think of it as a perturbation that's ongoing, because otherwise it would just be a model-dependent model. The responses of the star, whether they're hydrodynamical or chemical, in terms of just chemical reactions that will happen, they are all within the standard model. So they would all be baryon number conserving, what I call B and C. So the first assumption that I'm going to make is that the B and V processes, whatever they are, they're slower than the B and C responses that they get from the star. Basically, I want to have a quasi-equilibrium situation so that I can still use my usual standard model description of neutron star. The other effect that's highly model dependent is that if you produce new species of particles that are not originally included in the Lagrangian that you used to write your equation of state, then you're changing the equation of state in general. For example, if you use the standard model Lagrangian to find an equation of state, and then you consider the effects of an added term that generates this n to chi gamma, for example, then in principle, the chi particle could be produced, and it would contribute to the pressure and energy density, and it will change the equation of state. So we just have to get rid of it. So this model independent framework only works when the contributions to pressure and energy density from new particles that are not in the Lagrangian, which is different from being present, because being present in the star is about energetics, but I'm talking about the Lagrangian that you use for your equation of state. So the simple solution is to avoid accumulation of a dark particle if you have any new particle. So basically, we have two basic assumptions. The first one is that B and V rate is much slower than the responses from the star. Here, I'm symbolically showing them with gamma weak, but they cover a wide range of or different orders of magnitude of rates. The point is, the first assumption is very realistic, given what we already know from baryon number violation is already slow. So that's the first assumption, which gives us the quasi-equilibrium evolution. And the second assumption allows us to use the B and C equation of state in the absence of baryon number violation, which says if you have new states that are being produced that were not part of the original Lagrangian, they better disappear faster than the production rate. So as a result of this, in our framework, the state of the neutron star at any given point in time and on short time scales is actually just given by the original B and C standard equation of state that you started with. And the effect of baryon number violation is just the slow perturbation to the structure. The rate of change in baryon number would then uniquely determine where your neutron star is along its one parameter sequence. So to be more concrete and less abstract, I'm showing a few examples here. All of them could be valid within this framework. For example, neutron decaying to 3 neutrinos is valid because neutrinos, if they're low energy, they just escape. And if they're high energy, they might scatter once or twice, and then they still escape, and their chemical potential is 0. So there's no accumulation of neutrino at any point anyways, so they're fine. Dineutron 2 plus A minus could be also fine because the positron, which is the new state, first of all, positron could be already in the Lagrangian. Second, by definition, you know, its density is capped because it annihilates with the electron. And the third one, which we are currently working on specifically because of some other model building interests, for example, lambda decaying to a dark particle and a photon. This is only okay if chi decays faster than lambda decays to it. Okay, so these are all, these can all be considered. So basically, this is the picture, just pictorially explaining what happened here is that in the quasi-equilibrium evolution, let's say your star started from this point on top, it's going to just slowly roll down. And as it rolls down, it sticks to the equilibrium because of the quasi-equilibrium assumptions. And at any point in time, you can know where it is because you know what the baryon number violation rate is. And you can map it to all other parameters of the star because they're all at equilibrium. You can know its mass, radius, moment of inertia, everything else. Okay, so that's the basic idea. And numerically, we parameterize this rolling along the one parameter sequence with this eta parameter, which is just a derivative basically along the sequence. And it gives you the relative rate of change in any observable with respect to the rate of change in B. Now, of course, we use the numerical values, which depend on the equation of states when we actually want to get limits. But for the purpose of this talk, I want you to think of this as an order unity parameter. Okay. So this is, again, another picture just to give you an idea of what would happen in this framework if we had an active BNV channel. So this is just based on a BNV loss argument, basically. And these are independent. So they're turned on one by one. So if you had single neutron decays at the order of 10 to minus 10 per year, you would expect the mass to quickly fall down by 10 to 10 year. You know, it's predictable. And when it comes to hyperons, though, you see that the curves plateau, and the reason for that is that the baryon loss slows down because you run out of hyperons when you get to the lower masses. And so, of course, if we change the rates in this plot to a little bit lower, then you wouldn't be able to see these changes in the lifetime of a typical neutron star, which is about 10 to 10 year. Okay. Okay, so let's talk about some signatures. How do we actually connect this to observation? There are two specific signatures that I want to talk about. One is the individual pulsar spin down rate, and the other one is the orbital decay of binary systems. So the idea is that as pulsars spin down, if I have a new physics source of change in their moment of inertia, that would modify their spin down. And in the binary systems, if I have any changes to the components of the binary, they would of course affect the binary and its orbital decay rate. So both of these are accurately measured. And so we want to take advantage of that. So I'll start with the spin down. Pulsars do spin down mainly because they radiate. The most most basic and textbook example of it is if you had a dipole rotating, it will radiate electromagnetic radiation. And so that's the basic model for how they lose their energy. But when I write EM here, you can think of it as whatever your standard model of radiation is. So it could be more complicated. Our result doesn't depend on that because we're not actually using the error bars here. We're going to use the limit in the way I'm going to explain, which doesn't really depend on where did the spin down mechanism came from. The reason I say this is because pulsar spin down theoretical mechanism for it is still not well developed, and there's still issues in terms of describing this EM contribution. So, okay, so pulsar spin period and its derivative, so its rate of change in the spin period, are accurately observed. And if you subtract some extrinsic effects due to relative acceleration of the pulsar with respect to solar system, for example, which can be approximated, then you can get the intrinsic pulsar spin down rate, which is just the pulsar really spinning down, not just due to observational facts. Then it would be partly due to the standard radiation picture plus some new physics, which is BNV in this case. Now, we did some estimate of angular momentum loss due to baryon number violation. And we find that they're a few orders of magnitude smaller compared to other terms. And so we're going to neglect the angular momentum loss here, which means you can directly connect the spin down rate from BNV to the rate rate of change in moment of inertia. And so the way we get the limit here is we say that this new physics contribution has to be less than the intrinsic spin down rate. Now, in equation 9, it's not clear what's the relative sign between the standard contribution and the new physics contribution. They could actually have opposite signs. If they do have the same sign, then obviously the argument works perfectly fine. If they have opposite sign, I claim that this argument still works, because if there was an opposite sign between the red and blue term, then unless there is a fine-tuning cancellation between two terms that are not related to each other, theoretically, the intrinsic rate still has to, the BNV contribution still has to be at the same order or lower than the observed intrinsic spin down. Therefore, that's how we argue about our limits. Okay. So this is when we apply this to a pulsar, J0348, which is also, it happens to be in a binary system. The reason that we end up looking at a pulsar in a binary system is that, well, first of all, this is one of the most massive pulsars ever observed. It's 2 solar mass. And obviously, I'm picking something that's heavy because I want to limit hyperons. And I said, you have to look at heavy neutron stars that have hyperon to be able to limit hyperonic sector. The other reason is that usually if you look at isolated pulsars, it's hard to know what their masses are. It's just that when they're part of a binary, then we can actually measure their masses if we have enough parameters. So it's twofold. And so this specific pulsar has a companion that's a white dwarf. It's a very light white dwarf. And so, of course, you have to be careful if there is a connection between the pulsar and the white dwarf. If there's a mass transfer, ongoing mass transfer, then we can't rely, without knowing what that mass transfer is, we won't be able to say anything about the spin down rate. But based on the modeling that has been done for the system, we know the characteristic age of the system is 2.6 gigayear. And the white dwarf, based on its temperature, it shows a 2 gigayear cooling age, which basically means that the white dwarf has disconnected from the pulsar long ago. And the pulsar could be thought of as kind of isolated in terms of material transfer. So then we apply our method. And here I'm showing you the sensitivities to BNV rate, which is basically the limit I get on B dot, the model independent limit I get. And then I just divide it by the number of species that I have, let's say Neutron or Lambda, to just get a sensitivity estimate. Excuse me. So the limit on Neutron obviously is not as good as SuperK limit. It's far from that. In terms of it's it's like 21 orders of magnitude different. But the limit on the lambda decay is potentially 20 orders of magnitude better than Beijing spectrometer that I showed you. So there is a lot of potential in limiting hyperonic sector BNB interactions from neutron stars. And sigma minus, I don't actually think there is any limit. So terrestrially, I mean. So the other type of objects that I want to talk about is binary systems. I'm going to look at 3 systems here. One of them would have a pulsar and another neutron star. The other one would be a pulsar white dwarf, and the last one would be a double pulsar. So the idea is that this is now not the spin down, but the orbital period decay. So it's a little different. And so the idea is that the observed orbital decay is due to some extrinsic factors which are related to Doppler effects, relative acceleration of systems, so they're observational. But once you subtract that extrinsic factor, you get the intrinsic binary decay rate, which must be what's predicted by general relativity, basically, just the gravitational radiation. And there could also be some mass energy loss terms that you include. And so the new physics here would enter into this mass energy loss, as I'll explain. So the rate of change in the pulsar binary orbital period due to mass energy loss for spherically symmetric emissions of relativistic ejecta, it's called the Jeans mode, is given by equation 12, where you basically just plug in the mass energy of your components and the rate they change. And so the key is that if you look at equation 13, this could be due to rest mass change, moment of inertia change, or spin down. And so in equation 14, you can see that the change in mass and the change in moment of inertia, unless there's some other mechanism going on, which we're assuming it's not, are coming from BNV. And then there's the last term, which is actually standard. It's just due to the fact that the star is spinning down. So it loses rotational energy. So, okay, then we can combine them. So the energy loss term has a BNV term, which is given in equation 16, and a standard spin down term, which is given in equation 17. Now here, obviously, you can see that there are 2 terms. If you had 2 neutron stars in your binary, then there is a baryon number violation. You can assume there's baryon number violation in both of them, depending on their masses in equation 16. And so there is some degeneracy in terms of what you assume about what's happening. The systems we look at, they're either two neutron stars with masses that are very close to each other, in which case we assume that if there is BNV, it's basically the same in both of them. Or it's a neutron star white dwarf, where we assume that BNV is happening only in a neutron star. But the generalization is kind of obvious. Okay, so you collect all the terms from the standard contributions. Whatever is left is the room for new physics contribution, which is BNV. So that's the idea of getting limits from these binary decay rates. So these are the three systems. The first column is from Halson-Taylor, Halls-Taylor binary, which is the first binary ever discovered. So we have like 35 years of observation data, and it has a pulsar and a companion neutron star. Both of them are about 1.4 solar mass. Here in the third row, you can see their binary period. It's about 8 hours. I'm not showing all the extra digits, you know, for the precision here, but I'm putting the error bar to show you how accurately these are measured in the brackets. And so there's also an observed rate of change in P dot. That's the last row. The second column is the first double pulsar. So both of them are actually pulsar ever discovered. One of them is 1.34 solar mass. The other one is 1.25. This one is also famous for its precision in terms of measurement because they're both pulsars and they eclipse each other. And the third one is the same system I've been talking about. It's one of the heaviest pulsars, 2 solar mass. Its companion is a white dwarf, is only about 0.17 solar mass. And so again, my motivation to pick this guy also is because it's heavy, so I can talk about hyperons. Okay, so after we do what I just showed you, which is subtracting all the standard contributions, known contributions to this decay rate, the binary decay rate, we get the first row for these systems, which is 2 sigma. That is a one-sided 98% confidence limit on any new physics contribution that could lead to a P dot over B. Okay. So the next steps, again, are done in a model independent way. You just want to find the sensitivities at this point. So the second row is found from the first row, assuming all of the neutrons are allowed to participate in BNV. It could be decay, or it could be some other interaction. Could involve some spectator baryons. And so I just want to clarify that this doesn't mean that the reaction is actually happening in the star, because we haven't assumed a specific model. So you have to give me your model so that we can actually think about whether that's happening in the star or not, and at what densities. But this just gives you the sensitivity that you have. And it's actually the in-medium bound. So in principle, it's different from vacuum rates. And here, these are all n/a when it comes to limiting lambda and sigma minus. Because these systems are about 1.4 solar mass, they don't have any hyperons. Okay. But then again, you could see from J0348 that has hyperons, the limits are a little bit better than the spin down limit by about 1 order magnitude-ish. And they're still 20 orders magnitude better than what we know terrestrially. So the last step now, so we have this generic framework and we already know the sensitivities. What we want to do eventually is connect this to real models. So you have your BNV particle physics model, and you think of it in terms of rates in vacuum, for example. We want to map that to these limits. That's what we're working right now. So it's not finished, but I just want to show you a preview. So the framework we're using so far, which seems to be satisfactory, is just to use a relativistic mean field approximation because we're dealing with really high densities in the star. So in this approximation, baryons are immersed in a classical a background of mesons. Okay, so after you solve the equation of motion in the mean field approximation, you actually get a familiar form for the wave function of baryons in equation 21. It has a propagating wave because it's a uniform medium in the star, and it has a spinner part. The spinner satisfies a modified Dirac equation with a modified mass and a modified form momentum. Okay, so the only thing that changes is that your Dirac equation for baryon changes to something with a shifted form momentum and shifted mass. The shifted mass is called effective mass, m star, and the shift in the form momentum is baryon self-energy. And so I should comment here that the vector part of self-energy is actually 0 in the rest frame of neutron star's fluid by symmetry, but I'm just including it here for, because I want to write the covariant formulas for you, because you might be wanting to do the calculation in the center of mass of baryon, for example. So the important thing here, aside from just the formalism, is equation 23, is that the whole energy spectrum of baryons is changing now. So instead of having the familiar quadratic form, it has a constant shift by this sigma 0 component. And in this notation, sigma 0 is actually negative for the densities and the systems we're looking at. So the shift in the energy is actually positive. Okay. This is as opposed to if you were thinking about a baryon inside a nucleus, you think about binding energy, lowering its energy to avoid, for example, neutron decay. But this is opposite, and it's because at much higher densities that we're dealing with, the strong interaction is well in its repulsive side now. So this is really repulsive, and that leads to this shift in a positive shift in energy, as opposed to what happens inside the nucleus. So this is, for example, with our choice of equation of state, I'm showing you how the effective masses change as a function of radius for, again, the same two solar mass system. So you can see that the effective mass for neutron, it can be as low as 300 MeV in the core, but as you move towards the surface of the star, their mass gets closer to their vacuum values. Okay. Now, the reason that this doesn't get as close as to vacuum here is just a technical thing. I didn't include the crust of neutron star, but they get close to that value. Now, this is the important, I think the juicy part is that what happens to the rest energy of these baryons, because the rest energy is the energy available to the baryon for it to decay, for example, or scatter. So this is if I set the 3 momentum equal to 0 in that energy spectrum that I showed you. You can see that the neutron, for example, can have energies as high as 1150 MeV. Okay, so for reference, I'm showing the vacuum masses of neutron and lambda, just so that you can compare. And you can see that for radii less than about 8-9 kilometer, the rest energy of baryon is higher than its vacuum mass. Now, what this means is that you could, in principle, write a Lagrangian with a dark particle that is, let's say, 1.1 GeV or 1 GeV, and the neutron is allowed to decay to it in the neutron star, but you would never be able to even see that in vacuum or in a nucleus. And so in this way, and once we finish the rest of the calculations, we are able to limit branching ratios in a range of masses of final state particles that we would never be able to do in vacuum and nucleus. And just to show you this, I'm also drawing an arrow that says a new experiment. So if you're thinking about the neutrino experiments, the nuclei inside nucleus are bound, so they're not even 939 MeV. They're a little bit lower than that in terms of their energy. So the ones that are at rest. So the point is that the energy accessible to them inside in the neutrino experiments, it covers the energies lower than the rest mass of neutron. So because of this, we think even though our nucleonic limits are not as competitive as SuperK, let's say, in terms of order of magnitude, we look at part of the kinematical, we can look at part of the kinematical region that is not accessible by SuperK or CAMLAB. That's the point. So I'm going to conclude here, and then we can get to questions. I just was talking that neutron stars could be complementary to terrestrial studies of baryon number violation. There are obviously huge reservoir of baryons, and they could have high parons. It's still an open question, but if they do, the limits we get on the hyperonic BNV are much, much better than the terrestrial limits. And here we looked at a simple scenario of a quasi-equilibrium BNV that relocates a neutron star along its one parameter sequence. That's the typical sensitivity we get for orbital period decay rates is about 10 to minus 12 per year. That has to be interpreted in terms of neutron because it's the dominant species, but you can scale it. The limits from spin down are about 10 to minus 10 per year. So that's the order magnitude for the nucleonic channels. So now we're working on limiting specific BNV models so that we can finish this analysis and map all these sensitivities to specific vacuum rates and rule out, different classes of models. Thank you so much for your time.